Okay, can everybody confirm that they can see the opening slide there? Okay,
Yes.
good. I see two thumbs pointed in the upward direction. Okay, we're going to talk about bandpass filters, and it's a little bit timely because bandpass filters play an important part while we're in amongst each other, and we're trying to do contests such as a 7QP and field day and other things like that. So it's a good thing to remember. And also bandpass filters, like I was mentioning earlier, also play an important part with trying to block out some of the commercial radiation out there. So we're going to talk a little bit about what is a bandpass filter, and you'll see the acronym BPF or bandpass filter, types of bandpass filters. How do you use a bandpass filter? And I'm actually not going to end up, I missed this one. I am not going to end up including anything about designing and building bandpass filters. So this program's been a little bit abridged and doesn't contain all the little details in here because I knew tonight was going to be a big thing. So what's a definition for a bandpass filter? It's a device that passes frequencies within a certain range and rejects, and actually it doesn't necessarily rejects, but it will attenuate frequencies outside the design range. So here in the red below that, I have a nice little diagram. And the red there is basically representing the amount of signal that you're getting through. And the where it goes down on the low shoulders on the left and right side there, that represents that signal being attenuated, not totally rejected, attenuated. And we'll get into that a little bit more. So that area that's marked in B, that's the area that's allowing frequencies to get through. And the way you measure that is once you decide the very top of that, how much energy is going to be passed through that bandpass filter, we always measure the usable frequency at minus 3D from that very, very top frequency. That's just a little thing to remember, is that you don't just look at the flat top there. You always drop down about 3 dB, and that's the point that you end up measuring it. So types of bandpass filters. There's high pass filters that block frequencies that are too low, passing higher frequencies. So when it says high pass frequencies or high pass filter, that means it's going to pass the higher frequencies. The next below, low pass frequency, just the opposite. It's going to pass those lower frequencies through that filter, and it's going to block the higher frequencies. A bandpass filter is a hybrid of a high pass and a low pass filter, where it will block certain lower frequencies and it will block certain higher frequencies, but there's a sweet spot right in between there that's called the band pass. That's the frequencies that's going to be passed. So typically, this kind of a band pass filter, this type of filter, is going to be designed so it will straddle a particular band. In other words, like for your 80 meters, it will take and start blocking things, or low frequencies. It'll block it up to what, 3.5 megahertz, and it will pass the frequencies from 3.5 to 4 megahertz. And anything above 4 megahertz, it will block it. So it has that little notch in the middle, frequencies that it will pass. Now there's also another type of filter called a stop filter. So it's a band stop filter. So what it does, it's kind of the opposite of what a bandpass filter was. It will notch out a certain area, a certain set of frequencies, and it will block those frequencies past the higher frequencies, past the lower frequencies. And I'll get into where we end up kind of using this stop frequency. So a very typical use of a filter, of filters. So we talked a little bit earlier about AM broadcast. AM broadcast is a really kind of a nagging problem when you're trying to operate 160 megahertz. And so that's 1.8 megahertz up to 2 megahertz. And you're parked right next to the AM broadcast frequencies. So that's all those 100,000 watts, megawatt stations that are blasting out all kinds of RF energy. And they do a lot to clean up stuff, but it doesn't clean up everything. If you have a megawatt transmitter, it's not going to clean up 100% of everything that comes out of that broadcast station. So some of it's going to end up leaking through. It can bounce off of metal buildings. It can be re-rectified off of buildings that maybe are with aluminum siding and stuff like that. And that stuff can end up getting into the 160 meter. So typically what you do is that you buy an AM broadcast filter, and that will take out that AM band. So it'll block everything from the 550 kilohertz all the way up to 1.6 to 1.8. Usually they stop about 1.6 kilohertz. So wipe that, any radiation coming out of that, or attenuate it and keep it from messing up your 160. Guys that work the good old 6 meters, sometimes they're bothered by FM stations. And even sometimes 2 meters sometimes occasionally can get bothered by it. So again, you have a big high-powered station running FM. They're doing their best to clean up any of those little artifacts that come out of blending audio together and mixing products together in the process of producing RF. And again, this one here will be I have a band pass filter. It's actually going to be a stop filter. So that stop filter is going to end up blocking out the 88 megahertz to 108 megahertz. So that's a case where you're going to want to use a stop filter. I need to fix that. There's also things like for TV filters, and people know that people running on 10 meters or 6 meters, the older TVs and stuff like that, you can get into those TVs. Now that we've gone digital, this has pretty much disappeared and we don't have to worry about it. So let's talk about when and where we use filters. So we recognize that in our radios, there's a lot of filters built into it. For transmitters, there are bandpass filters. So very typical, your transmitters, they make little birdies and they make little harmonics, and not all of that can get cleaned up, especially if you're in a close area. Not all of those are going to be cleaned up. And so typically you'll have bandpass filters in there for each band that you're operating in to clean up all the dirty RF that is being created by your transmitter. Receivers in our radios, there's also bandpass filters in that. One of the things that we recognize is that if you have a really strong station that's up close to you, that RF, it may not be in the bandpass that you're listening to and you're trying to take and process, but it's strong enough where it can overload that receiver and cause that receiver not to function correctly. So overload that front end and keep that receiver from doing what it's supposed to do. So a lot of the new receivers have good bandpass filters in the front end. So if you're on 80 meters, it's going to block out all the other frequencies as best it can on the receive side all around that particular band. So let's see. Yeah, okay, we already talked about broadcast interference and using high pass filters in there. Really important on 160 meters. It's hard to get if you have any. It's really hard not to have use a broadcast filter on that. And likewise, still on your FM broadcast, that's referred to as a stop band filter. Okay. Contesting. So if you're in a big group of guys, like on 7QP field day, and you have all these wonderful transmitters that are transmitting, those transmitters are going to do their best to take and clean up what they're transmitting. And you also want those filters because it's going to keep you from receiving, or that receiver from being overloaded by an out of band frequency. So that bandpass filter is going to set on the front end of your transceiver, and it's going to only look at or only allow frequencies in and out of that transceiver that's within that bandpass filter. Very important concept there. But you have to think about it working on both the transmitter and the receiver side. Okay, so here's a typical bandpass filter. And I mentioned before that a bandpass filter is really made up of two filters. You have a low pass filter and you have a high pass filter. And then you have a little DMZ zone in between where all those things are built and configured that allows that frequency to come through that you want to come through. So if you're on 40 meters, it's going to block all the lower frequencies, it's going to block the higher frequencies, and only let those things that come through that is in that band pass. So again, this is an ideal view of what that filter looks like. On a bandpass filter, you can see that it cleans up, doesn't let anything through on the lower frequencies, like your FL down there. Anything on the higher frequencies, that's frequency high, it blocks all of that stuff. And again, it doesn't necessarily block it, but it attenuates it. I'm going to skip this one here. So let's get to some really good, interesting stuff. Here's a picture of a bandpass filter. So this is using a VNA to profile it. So I'm sweeping the thing with a set of frequencies, I think from 80 megahertz down to 15 megahertz is the ones that count. And you can see the little flat top at the very top of that. That's the area that's going to let the frequencies in on 40 meters. Yeah, that's a 40 meter bit. So that's what's that? 7 point. Come on, what's 40 meters? Yeah, 7.3 megahertz up to come on. Yeah.
Be 7.125 to 7.3 for the phone band.
There we go. There we go. That's what I needed. And so that's it's spread out a little bit too far, but I think you can kind of get the gist of what that looks like. And where we measure that for how much is going to come through is at that -3 dB. So that's going to be very close to that first rectangle up there. Now this is actually a pretty darn good looking filter. This is one of the better ones. But also when you go out there and buy filters and grab filters, it's amazing what you can find. So we'll get into that in a little bit here. So bandpass filter is typically a combination of high and low filters made from capacitors and inductors. So when you take one apart, you'll see all these little capacitors and inductors in there. There's stuff online you can actually get to, and you can design filters and figure out what the right values are for these particular filters. These types of circuit, depending on frequencies, very dependent on frequency, has about a 70% efficiency. So insertion losses, whenever you put one of these filters in place, you're going to drop between 0.5 to maybe 2 dB worth of information, RF going in or going out of it. So when you put one of these things in line, it's not like it's a perfect conductor. Bandpass filters that have steeper skirts and are more efficient in giving you good rejections are going to have higher insertion losses. So just think about that as you get better and better bandpass filters that do a better job of filtering out stuff you don't want to listen to. You also have to pay a penalty by a little more insertion loss. So places that you can find bandpass filters, the Ray Solutions has a whole bunch of Dune Star. I think we have some of those. They're up in St. Helens. DX Engineering is a great place to find them. Look around, there's many other providers. If you like doing kits, you can find kits out there online for building bandpass filters if you would like to do that. Prices for a bandpass filter, and this is for 100 watt. Remember that you're going to be transmitting through this. So that filter and all the components in there have to be able to handle the power. So for just a regular old transceiver, 100 watt, you're going to pay anywhere from 90 to 120 bucks for those filters. Now, if you're going to be running high power, those filters are going to cost you between $300 to $500. A lot more expensive. They're bigger pieces of aluminum. All inductors and capacitors all are made for carrying high amount of current and higher voltages. So I started at the beginning and I pointed out that these filters, they're not blocking things. They will unwanted RF. They're going to attenuate RF. So a good filter will attenuate unwanted signals by about 20 dB. A really good one is going to get you down around 70, 75 dB. But that's going to be a much more expensive one and probably with a greater amount of loss in that. But all you're going to do is get probably, the common garden variety one is going to give you about a 20 dB worth of attenuation on unwanted signals. So it's still possible when you're in close proximity with big transmitters and stuff like that for stuff to leak through. For really high levels of attenuation, it will take multiple stages of filters. So that's another way that they do things. For getting really good attenuation, they will run stuff through multiple levels, both at the high pass and low pass into that to get things down into that 60, 70 dB area. So one of the things when we start looking at these bandpass filters sometimes can get kind of wide and they may be passing things that may not be undesirable. And the skirts, the sides of the filter, they also can be pretty wide. There's a lot of variability. And so one of the things I did, I grabbed a bunch of bandpass filters and I ran them through my VNA to try and take a look at them. So here's an interesting one. And the reason I'm giving this is really to give you a picture, is that these bandpass filters is not like that first 40-meter one. That's an exception, huge exception. The stuff I'm going to show you now is more of reality. So you have to understand that these guys aren't perfect as far as how they attenuate signals, how much attenuation, the skirts that you have on it, and the efficiency losses that you have with these things is not real good. And one of the things on these next set of slides here, I did not draw my reference line to show you the amount of loss that you have on there. So I didn't show you the power level that was going into the device. So the good old marker 2 and marker 3, that marks the 40-meter band. You can see that both on the low side and the high side, it passes a fair amount of energy into that through that filter. So everybody kind of get their head around that. Is that marker number 2 is the low end of the frequency for 40 meters. Marker number 3 is the high end, and that black line is the energy on the left side is how it gets attenuated there. You can see it's a long slope for the skirts, same way on the downstream side. So it will pass things that you may or may not always want. Here's a good one for 80 meters. This one here was pretty sickening. I think this was a damaged bandpass filter where the high pass was screwed up on it. So again, marker number 1, that's the beginning of the 80 meter band. Marker number 2, that's the end of it. You can see all of that upper end of 80 meters, it's all being attenuated in there. Not nice. Really not nice. So this one here, I think, is more like this is a broken bandpass filter. Oh, here's another one to think about. Let's say you have a 40 meter bandpass filter in there and you're trying to operate on the 20 meter band. You try doing a tuning on it. You try doing transmitting on it. What kind of results are you going to get? You're going to get the results you're going to get is a horribly high SWR. You're not going to be able to hear anything, and you're not going to be able to tune anything. Your transmitter is going to be very, very unhappy with you. And if you force the issue, you will end up damaging a bandpass filter. Here's a 10 meter bandpass filter, kind of the same stupid plot here. But 10 meters is a huge band, and you can see the marker number 1, that's the beginning of 10 meters, and marker number 2 is the end of it. And you can see that this bandpass filter is chopping off a whole lot of usable 10 meters. Here's one for 20 meters. I'm sure you're probably either confused. I was absolutely shocked when I was going through these, and I rechecked them on a different VNA. In fact, those little $50 and $120 VNAs, you can do exactly the same thing here. It'll do exactly this kind of chart for you. So most of us have one of those things. So we have the power to take a look at any of our bandpass filters and see what they're actually giving for us. So anyway,
if you have a spectrum analyzer with a tracking generator is the traditional way to create these.
Yep. Well, I'm trying to get it so us common people can do it. So here again, this is 20 meters. Marker number 1 shows the beginning of it. Marker number 2 shows the end of it. So, I mean, you got a good almost 10 dB worth of about 8 dB of loss here at the beginning of the band before it gives you through full throughput. Okay, so just about to the end of this, talking about poles. Number of individual active components within the filter. So, and it's usually a pair of them. It's usually a capacitor and a coil. And so that kind of represents one filter unit, and that's kind of generally referred to as a pole. Generally, the higher the filter order or the number of poles, the steeper the slopes, the skirts will be. And also you'll have a little higher attenuation too. Well, you obviously have a higher attenuation on the skirts, but you will also lose a little bit on the center as far as frequencies you want. More reactive components means greater insertion loss. So the more poles, the more active components you got in there, the more you're going to have some losses. Okay, field day. So field day, I think everybody's experienced it enough where we always have bandpass filters around. We pretty much drill it into everybody that you kind of figure out what band you're going to operate on, and you check out a bandpass filter for operating on that band. And that keeps us, ugly transmitters from transmitting any kind of garbage out there that scrambles things for everybody. And also on the receive side, it keeps us from receiving a bunch of extra high-powered garbage that may end up affecting our receiver there. So when we do contesting, it's always on 160, 80, 40, 20, 15, 10, and 6. 6 is sometimes optional depending on the contest. but those are the primary contest bands that we have out there. We don't do any of the 30, 60, 12, 17 meter bands for doing contesting. Filter goes between the transceiver and the tuner or amp. If you have a high powered bandpass filter, now that last bullet there was for low powered stuff for the 100 watt guys, or the 100 watt type of bandpass filters. If you're lucky enough to spend the extra bucks for the big guns out there, those bandpass filters will go after the amplifier. So
Hey, Mike,
here's a couple. Yo,
could we go back to that slide? I think it's worth mentioning because it's an easy fail. And I've seen another club that I belong to burn up a few. So many of our radios have internal tuners. And when you just plug in and you're not really thinking, and you could literally hurt the filter, damage it, or kill it. You need an external tuner to get the bandpass filter between the radio and the tuner. You can't use the internal tuner in the process of trying to do this because it just won't. It's not physically impossible to open up the radio and stick the bandpass filter between it and the internal tuner. So please, if you're planning on coming to field day or 7QP, make sure you have an external tuner so that you can put the bandpass filter between the two.
very good point. Very good point. That's something I didn't think about adding in here. But yeah, having that bandpass filter on the outbound side of your tuner will end up scrambling the eggs. It won't work right. Okay, so here's a couple. If you like doing yourself stuff, you can do. There's calculators out there to do stuff, and there's plenty of kits out there that you can buy these things if you want to do it yourself, or you can get online, and there's plenty of resources there where you can purchase things. So let's wrap this things up here. Okay, filter. Okay, passes desired frequency, blocks or attenuates unwanted frequencies. So however you slice and dice it, that's the main process of what you're trying to do using a filter. So many filters are built into our transceivers. Some are required by the FCC. You basically have to have these filters there on the transmitter to keep things clean enough to pass your type acceptance for the FCC. Many filters improve our user experience. So they're, if you have a AM broadcast filter, so that cleans up things and makes our experience a lot nicer. Special filters can block broadcast interference. When contesting with large groups, bandpass filters are required for each station. So that's going to finish up my program here, and I expect that there'll probably be a fair amount of discussion. So
Can I make a couple of comments, Mike?
Please.
My big one is that bandpass filters are not magic. If you have a cruddy transmitter, a bandpass filter is not going to make your cruddy transmitter into a good one. And the reason I say this, and this isn't to hurt anybody's feelings, but if you have a little FT817 or FT857 or IC7000, that's especially one of the all-in-one tiny little rigs, their transmitters, because of the space considerations and the trying to be everything to everyone, the transmitters are not especially clean on those. And yes, the BPFs can clean those up a lot, but you'd much rather in those environments with field day or 7QP where you have multiple transmitters close, have your rig that has the best transmitter in it, not your rig that has the worst transmitter in it. If you're up in an FT7 or a IC7000 or an 817 or any of those rigs that I mentioned, the little ones will do just great if you're up in the mountains alone or whatever, if you're not, in a place where you've got a lot of transmitters in the same place. But I highly do not recommend that for either for 7QP or field day that you bring any of those all-in-one rigs. They tend to splatter all over the place, even with the BPFs on them. So, and also note that bandpass filters don't help you within the target band. So a bandpass filter will not help you run CW and sideband on 20 meters simultaneously. It can be done, but you have to have, again, rigs with transmitters that are clean. The BPFs don't help you out a lot with that.
Yep.
My other comments are just surrounding the shape of the curve at the top is usually called ripple in filter design. And filter design is all trade-offs. So you're trading off the ripple versus the steepness of the skirts versus the insertion loss. This isn't only something you do for analog filters, it's also done for digital filters as well. So we actually, from the digital side, have digital design tools that we go through, and we can put in all the parameters for the filters, how many taps. I'm trying to remember what Mike called them. We call them taps in the digital domain, but they're
Poles.
yeah. Poles, yeah. Taps are the same thing as poles. How many taps you have in the filter. And the ripple, we can't actually in digital come up with a perfect filter because of rounding. The rounding error actually causes a lot of that imperfection in the filter. So just remember, when you're shopping for filters, you're always looking at design trade-offs between latency, because the filter parameters will also cause latency. It's usually not a problem for sideband or CW, but if you're running some tight digital modes like Vera, your latency can make a difference in your filter going through it, et cetera, and so forth. So those are my slightly technical comments about bandpass filters and everything. If you would, just to brag, if you would like to see a huge full power bandpass filter, there will be some at 7QP on the back of my linear amplifier. So I have at least ones for 20 meters, and I think I'm going to buy another one for 15 just in case.
Cool. Anyway, very much agree with everything there.
Another comment, filters are mechanical. I mean, their inductors are wound up piece of the wire, and if you drop them or bang them, they can get knocked out of shape. Some of those pictures that Mike showed look like filters that maybe are mistuned, possibly from rough handling.
Yep.
And some of them can be adjusted. Some of them have adjustable capacitors and such inside that you can tweak them a little bit. So you can possibly bring some back if they're out, but you want to be gentle with them. You notice that, like, the club ones are stored in a box with foam all around them, so they don't get banged up.
Yep.
Another thing people may be interested in that's slightly, getting afield is that filters aren't the only the necessary way to deal with some of this stuff. Some of the newer technology that's coming out are things like adaptive pre-distortion, where we actually sample the signal digitally, figure out how it's distorted on the output end, and then we distort the input on purpose in order to correct for the output distortion, and then come up with a signal. And you can get anywhere, you can get literally 20 dB worth of suppression of your harmonics by doing that, which, again, cleaner transmitter to start out with makes everybody's life easier. So, and you can do it on that's why a lot of amps you see now will have a sample port on the back of the amps. The experts have them, our amp has them, Flex Radio's amp has them, a couple, I think Elecraft's amps has them. And that's specifically so that you can use these adaptive pre-distortion techniques so that you can sample it on the output side of the amp and correct for the whole signal chain. So those are some things that you might be seeing in the future to try and correct some of these issues as well. And the great thing about that is there's really no loss to that, right? You don't get any insertion loss by pre-distorting your signal.
That's a big deal on that. That's a really important thing. It's too bad we don't have more radios out there that exciters that actually provide that feature.
Yeah, point taken, Mike. It's in the hopper.
A lot easier to do in the digital world.
Easier is the key point about that.
More like possible at a practical cost instead of impossible. Not quite impossible, but very expensive.
Mike, this is Scott here. I don't think you guys see my video. Camera's not working right now. I got a question, and maybe Anna can also weigh in on this. Anna, by the way, thank you for pointing out about the digital filter insertion loss. I was wondering about that. Because I didn't know whether digital filters suffered insertion loss in a literal sense, but I guess the algorithm, I mean, the way the filtering works, that there is some suppression of whether there was loss in a digital way, I suppose.
The funny thing is that there is loss, but then you just multiply the signals up and you get the gain back.
Gain
So
back.
Okay, that's easy.
It affects
okay.
your resolution and precision when you do that, but yeah.
Yeah, no. Well, my question is more about the the danger of tuning, putting the tuner after the filter after the tuner in a normal installation. I was wondering why, why you actually damage the filter. Is it high SWR? I mean, if you're tuning within the bandpass of the filter, why would that damage it?
If it's within the pass band, it's not so bad. If it's outside the pass band, when you attenuate a signal, you're turning all that energy into heat. So you're trying to cook the inside of the filter if you're outside the pass band. But anytime you're tuning an antenna or tuning a transmission line, you can be generating some pretty high voltages.
Right.
And you might be putting, 1,000 volts into a filter that's just not designed to take that.
Right, that's
Well,
what I was wondering.
the filter is designed for 50 ohms. So if you're putting it on an antenna that's not, you're going to end up with reflected power getting reflected back into it and all sorts of nastiness there. So you'd rather not have that. You'd rather tune afterwards, and that way your filter is within the 50 ohm chain rather than the high or low impedance that you've got on the other side of the antenna. Now, if your
Right.
antenna is perfectly matched anyway, you don't really care because you don't need a tuner anyway. But yeah.
Right. But that's what I was wondering. What was the root cause? So it is the highest WR that could possibly be there if you've got a big mismatch.
Incidentally, that's what bakes antenna tuners too. If you've got high power into antennas that are a bad match, all that energy has to go somewhere. A lot of it is high voltages as well, and you end up arcing between the inductors because it's usually a whole bunch of air wound inductors sitting in there.
Sure. Yeah, because I know that basically filters really work by creating a high SWR when in the stop band. Let's say if it's a band pass, either side of the band, the pass band, there's a high SWR that's actually created. So what's going on is they're rejecting all the frequencies that are outside of the pass band by actually reflecting them back to their source. So
well, it's not necessarily a high SWR, it's attenuation, right? So you can have a 50 ohm attenuator, it'll have a perfect 1-to-1 SWR, but you'll lose all your power in it. So these things are setting up attenuation on places outside of the passband.
right, that's resistive attenuation, but these elements are all reactive, right? So they're not supposed to burn up any power. So I'm reading about filters now in a deep way. So what generally is discussed is actually the VSWR at the input and output of the filters. So yeah, they're designed for 50 ohms, but if you're outside of the passband, then the impedance is going to be much higher than that, and usually you won't get a good match to a 50 ohm amplifier, say in the chain before or after input to the output.
This is beyond me, this
Yeah.
discussion.
What's that? Oh, well, anyway. Yeah, I'm sorry for going off on a tangent there. But anyway, thank you for that. I wasn't sure what the reasons were, so okay.
I've got a question. And thanks for this presentation. I've been trying to figure out how to do something, and which is in my attic, I have a couple ham radio antennas and a Yagi TV antenna pointed in a different direction. But they're close enough that when I transmit on VHF, the amount of signal coming down to my TV is enough that I haven't done that when my TV is plugged in, because I don't want to burn up my nice Sony TV. So I've been trying to figure out how to protect the TV from the VHF signals, because the ham radio band is right in the middle of the digital VHF stuff. So it looks like maybe a band stop filter in between my TV and my Yagi antenna would do it. And I'm wondering what to look for, and also how to measure like how much power is getting to the TV. And do you know, like, at what point would that amount of power be something the TV can just totally handle with no problem, and how much power getting to the TV is like potentially harmful?
Probably not much power would be harmful.
Yeah, I mean, every TV manufacturer is going to be different on how much it can withstand.
Mm-hmm.
But that can be a real problem. Mike talked about a filter having 20 dB attenuation. That means if you put 100 watts into it, you're going to get a watt out.
which
And
is still a
watt
lot.
is a huge signal for a receiver. Yeah.
Right.
Well, and you might also want to think about, and this is something that essentially repeaters do, right? Is two filters, one on your ham radio, one on the TV, and then you get kind of double coverage there. You have a band pass filter on your TV to filter out everything outside the band, and you have a band stop filter on your ham radio to get rid of everything that's inside transmitted inside that band.
Oh, because
And that
what I
might
got to
help
worry
you out
about
better.
on my transmitter is the harmonics that aren't the ham stuff.
Correct. That's
It's
what you
gonna
would
hurt
be
the TV.
receiving on your TV, right?
Got it. Got it.
But you can, it's the same problem that you have at a multi-site. The RF, even if it isn't at the band the TV's tuned to, can be a strong enough signal to upset the front end of the TV. You might
Got it.
want to look at what TV stations you're listening to. There used to be some below the 2-meter band and some above,
Mm-hmm.
but a lot of the lower ones are gone now.
Oh, right.
So
We
you
pretty much just
might-
watch OPB. Maybe I just get an
Yeah.
OPB bandpass filter and reject all the others.
Well, that's a problem if you're in Corvallis because they're on channel 7, which is in the lower
Ah,
frequency range. But you could pick up 28 out of Eugene or Lebanon or somewhere. I get two copies of 28 here.
Hmm.
They're up at a higher frequency.
You
Okay,
probably would like to do some math on this if you're really concerned about it. Remember that it gets worse as you get higher power. So for me, I ran into a lot of problems because I've got legal limit, right? That's 61 dBm. Even if I had a band pass filter that's 60 dB, right? That's a lot of power that is still getting radiated that's off band. That's one of the reasons why BPFs become even more necessary when you get higher in power. But there are converters online that you can convert to dBm. It usually makes a lot of sense that you can use those to figure out what your transmitter out power is, how much attenuation you're going to have on your bandpass filter, and figure out how much that's really going to be on the receive end of things as well.
Cool.
Because we figure out transmitter their ratings, and I don't know if it would be easy to get for a standard TV, but their ratings about what their overload is for in dBm.
mm-hmm. Is there a cheap way if I to double check my math to actually measure the input that's coming into the TV and get like some kind of quantify how much power is coming in?
Well, yeah, usually you call that a receiver.
Okay.
Yeah, the cheap ways are receivers with a signal strength meter, but you run the same danger of they're sensitive to overloading as well.
Here's an idea. If you get an
Yeah.
RTL SDR, they're $15.
There
You
you
don't really
go.
care if you destroy the receiver on those things, and they're
Yeah,
right in the TV band anyway.
Oh,
That's
perfect.
the kind of thing you want. And the other thing you can do is you can put an attenuator in there first and cut the signal way down and measure it. And if it's low enough, then you can take the attenuator out and measure it.
That's like
Try to avoid burning up your detector.
mm-hmm.
So let me throw one last thing and then let's kind of move on here. So I have several receiving antennas. Those receiving antennas are absolutely superb for picking up all of my RF that I generate with running full legal limit. So before those things come into my receiver, I have a little front end device there, and you can kind of think of it as a Zener diode, where it will allow a voltage up to a certain point. Once it gets above that point, then the Zener starts conducting and grounds it, or not grounds it, but doesn't let that voltage get above that. So there are devices out there for receiving antennas, and I have no idea how appropriate that is for higher frequency stuff, but that's a very common way of protecting receivers to make sure that they don't get overloaded by transmitters. You kind of understand what I'm talking about there?
Yeah.
Okay, cool. And DX Engineering has those that I know. You take a look on the DX Engineering website. They have one for all the HF stuff, and I don't know how high that goes as far as other frequencies. Okay, any other subjects before we get back to business?
No, Anna's gonna shut up before she takes up the entire meeting.
Thank you, Mike. Thank you for the lively discussion from everybody. I've seen them, Scott and I recently in the same location trying to operate two different bands, and we saw how effective they were as far as not having one and then suddenly plugging one in and the other station is now allowed to operate. So I'm not going to go into detail. We've had enough discussion about it, but they do work.